everyone, and welcome to the latest edition of the Big on Small podcast, which is now going external. Welcome to our new audience. Thank you for those of you outside of Malvern Panalytical that heard our last podcast where we were preparing for our summer holidays with our sunscreen, with our sand, and and ensuring we're not being exposed to the wrong things in the environment. Of course, being external brings some new challenges to the three geeks that we have here, Taco, Steve, and myself, Paul. And because there's one thing that joins us all together, and hopefully you, our audience, is we just love science, and we love the science we get involved in here at Malvern Panalytical. And just talking about what we've been reading about and have noticed in the scientific press and in the general press over the last few weeks. So with no more to say, I think it's time to get going. What do you think, guys?
Yes,
good
idea.
And I don't know about you, Tucker. I can think of no one who can set us off on a safe direction, safe, standardized direction than Steve. Steve, start us off in the right tone for our audience. Go for it. What have you discovered this over the past few weeks?
So I've decided to talk about politics.
Oh, Steve, it's in the list of 3 things that you should never talk about in public.
But politics and particles do go together, which is one of the things I've been finding around. But I will be trying and not offer a good or bad views for particular things. So what I'm actually going to talk about is air pollution, or air pollution really caused by particles. Because there's been quite about 4 or 5 interesting news stories in the last few weeks. It's being blamed for lots of things at the moment. It's supposed to be potentially a big spread of antibiotic-resistant bacteria in the PM 2.5, which is the particles less than 2.5 microns. And the same fraction is also being blamed for dementia and cardiovascular issues. So it's not just lungs, because everyone thinks soot goes into the lungs, causes bronchitis and asthma, and it does, absolutely. And that's really the less than 10 micron fraction, but it's the less than 2.5 micron fraction which can get into the brain, because it will enter the bloodstream at that particular size, and can be responsible for dementia. But what I really wanted to spend most of my time talking about was pizza.
Pizza?
Because, yes, there was a...
Don't tell me pizza's bad for the brain now. That's Friday evening.
Well, it ties in again with politics and pizza and particles. Because it was the New York City Council had put some kind of mandate on various pizza joints that they had to really control their particle emissions. And a lot of people who I won't name or say, had weighed in of saying that they're trying to blame these pizza joints for global warming and to put this expensive device on it to reduce their carbon emissions. And this will do nothing to help global warming. And that is completely correct. I may not agree with the politics of these people, but it will do nothing for global warming, because it was nothing to do with carbon dioxide emissions in the first place. It was to do with carbon emissions, not carbon dioxide. It's soot. So it was a lot of wood-fired pizza ovens. That 100 pizza joints aren't going to contribute to global warming, but those 100 pizza joints could cause health issues to their community by not putting a kind of devices on there. So it was about the people's right to wander around in their neighborhood without getting lung diseases, and nothing to do with global warming. And people were saying, it could change the flavor of the pizza, putting this device on, which isn't. All this device is, it's something which is where our kit gets involved in too, called a scrubber. What a scrubber is, it's something which can fit on a flue, which is the hot air, which has got some particles in, which has come on the back of the oven. And it's got a series of water jets of certain sizes. And the particles in the gas rise and they get hit by the water jets. And it knocks all the particles down where they can get collected. And the master size has been used for testing the efficiency of said scrubbers, and kind of make sure the water jets are the right pressure in the right place, so we can look at the particle size of that. And the same scrubbers, in slightly bigger to what's in a pizza oven, also get used by councils when they're burning waste for energy. So it's a bigger scale because, again, that could be a major issue from those particles. But those particles, when you're burning waste for energy, bring another of our techniques into there, because when you're burning waste for energy, you could also inadvertently release heavy metals in as those particles, things like lead and zinc, which, I mean, we've talked about carbon particles being bad for you. Micron-sized particles of lead, metals, which are in and zinc, inhaling those is going to be even worse for you than carbon. So XOF has also got used on the outputs of the scrubbers for checking the elemental composition that these things are burning. So. But I mean, there's a lot of people try and politicize these things, but it's not really. It's just a chance to put some cool technology on these pizza ovens to knock the soot out. Doesn't change the flavor of the pizza. Makes it more sociable, so everyone can still enjoy the great pizzas they want. But we're removing the bad particles out of the exhaust flames of the oven. What's wrong with that?
But Steve, there's something totally different angle coming in here, and watch out for this argument. So all the vessels cruising the oceans, they were emitting a lot of sulfur dioxide and soot. So they banned the sulfur dioxide from percentage levels now to below 1%, and also the soot comes down. And now they say the oceans are warming because the soot is not blocking the sun anymore, and therefore the temperature is higher of the ocean. It's an amazing story for me.
Well, they must have been producing a heck of a lot of soot for it to cause blocking out of the sun.
It's interesting, the connection between different arguments, but I guess the point here being about how you apply your science and what's appropriate science. So that jumping on the onto the climate concerns and carbon emissions, if you don't really there can be some misunderstanding about that I guess came into it, and it starts being used as a label everywhere. So
people got their forms of carbon confused. Carbon soot particles are not the same as carbon dioxide. As Taco said in our last podcast, there are different forms of carbon, which we covered last time. And carbon dioxide and soot are again different forms of carbon.
And diamonds are not in the sky. In this case.
Well, no.
People wouldn't burn diamonds either. Yeah, and not inhalable.
So good that Malvern Panalytical were involved in the solution to ensuring the good people of New York can keep their pizzas, but also a responsibility there for scientists to be careful about how we apply and how we communicate our science as well. So where does that take you, Taco? What did you see during the week or during the last few weeks?
Amazing insight in our health. So I was a bit scared when I read the article about that the bacteria get more and more immune to our antibiotics. And we all know that by hospitals and people more, but it has to do with microplastics, which was like, where is that coming from? So what the thing is, and before I go into really deep into the antibiotics, bacteria, and that kind of stuff, I think it makes sense to tell a little bit more about where microplastics come from. But I'm not sure if people will realize it. But what do you guys think are the biggest emitters of microplastics?
Ooh. Washing all my shirts at the end of the week. How about that? What do you think, Steve?
I was thinking laundry as well.
No. It's it took me when I say it, you will realize it's tires. Tires are the biggest. Tires, yes. The wear of the tires, because we have so many cars, and even with the electrical cars, they are more heavier, so they wear more tire. So, and the microplastics from tires are the biggest source of microplastics. Second is packaging. So a lot of packaging we use, and and when they are processed, they produce microplastics. And agriculture, there's a lot of plastics in agriculture going on for packaging. So, but people were wondering, okay, so this is the source of the microplastics, but actually which plastics and polymers do produce the most microplastics? So they made a microplastic index. And that is the likelihood of a plastic type to produce a microplastic, an MPR. And it is and also the size of the microplastics. It's the opposite of the tendency to produce a microplastic. So there is a whole graph from polyethylenes to polypropylenes to PET and to all kinds of stuff, to PMMA, polymethyl methacrylate, which people don't probably know, but it's used in car backlights and more the brittle plastics. So that has the highest tendency to form microplastics, but the smallest particle sizes. While on the other side of the scale, the packaging materials for polyethylene and polypropylene, they make less microplastics, but very large particles. And in the middle is the PET bottle. We all know from the water bottles. It is an average tendency and an average particle size. But so if you know that, you can adapt your packaging and your plastic to what's the amount of microplastics you want to get. But eventually, all these microplastics get into the environment, and that's where the not so fun starts, because these microplastics are not as such in the environment. Everything grows on there, and also bacteria grow on there. And these bacteria, when they and the microplastics in the sewer. And so they encounter all our, but also the medicines we swallow, the contraceptives, and there is heroin, cocaine, there's everything in the sewer. And that mixture makes these bacteria more resistant to antibacterial medicines. So that is they discovered, and that was my finding of this week. I was really surprised by that. So that our bacteria we encounter are getting more and more immune because of the sewer, the microplastics in the sewer, because it's a perfect growing medium with all this surface areas around it. So that was amazing finding for me.
And I suppose there's a connection between what I was saying and what you were saying when you look at, say, car emissions in various kind of neighborhoods as such, and talking about sort of general air pollution, because if you can control the speed limits, you can obviously help control the kind of emissions, but also the amount coming off tires. So the higher speeds you go, the more will come off the tires. So by I guess below traffic neighborhoods ideas, which obviously does get heavily politicized by people, but it does have some health benefits.
Exactly. Yeah.
Nice. It also shows the importance of the particle size. Particles get smaller, their surface area increases, and that drives all sorts of processes. And we can talk about important processes like catalysis in industry, helping us create drugs, some of the ones that you were talking about. But also, what does it do within the natural world if we have particles of those sizes? And really, scary thought that leads to bacterial populations blooming, and as a result of that, gives a mechanism for increasing resistance. So where do we get involved then, Tarka, in all of that?
Yeah, so measuring the particle sizes, and what also is very encouraging and motivating for me is that we're part of the Momentum project, which is doing toxicology investigations on microplastics for health. And therefore, the word I learned, which is really a fantastic word, it's a frustrated macrophage. I really like that word. I mean, it's a kind of cell which tries to eat microplastics in the lungs, but the microplastics are too big and it gets very frustrated, and it sends out all kinds of chemicals which are bad for the body. But it sounds so funny. It's not nice, but it sounds really funny when you have a frustrated macrophage. Yeah.
Fascinating. And again, linking it back to what Steve was saying about the response of the body in this case, leading to other issues. So not only resistance to antibiotics, but also the response for the people with asthma and things. So I'm loving this because we're starting to get a connection between us all. But I ended up with, as you'll know, Steve definitely and Tarka, I love in Modern Panelistical this phrase, seeing is believing. It's something that's always I always scratch my head and wonder whether that is maybe because my eyes don't work too well, so I have to see through a pair of these like you guys do. But it was interesting. I was reading an article in Chemistry world. And one of the people there posed the question is, when did scientists believe in atoms, or when did chemists believe in atoms? And was a really deep article about what's the purpose of science and when and how does it resolve things over time. So I think it does link into what we're talking about. You guys were talking about, how do you apply science? How do you do it realistically? How do you build models or understanding that help people? So in this case, atoms, they were proposed a long time ago as Dalton, who suggested that materials could be distributed as either atoms or connected together as molecules, and he saw it as a model for trying to understand the properties of materials and how they differed.
When was that?
So that was back in the 1800s.
Okay. Yeah.
But in terms of proving that, we move forward to the work of John Perrin, and he proposed that if molecules really existed, then in a liquid they would be uniformly distributed. They wouldn't all sink to the bottom of a vessel, and if they were uniformly distributed, then he should be able to work out how many of them there are. And the way he did that was through Brownian motion, and he was able to make observations of the movement of known sizes of particles under Brownian motion, and from that linking to the Stokes-Einstein equation, so one of the most highly cited works of Einstein. He was able to not only he was able to then calculate a value for the Boltzmann constant for the distribution of energies of the molecules, and from that calculate Avogadro's number. And Avogadro number, it gives you the number of atoms in a mole of material, a fixed a standardized amount of a substance. And what was really interesting was that the number that he arrived at agreed with the same number calculated from other techniques, such as light scattering, or looking at radioactive decay, or looking at black body radiation. And he therefore postulated that it was highly unlikely that if all of these other measurement methods came up with a similar number, it was highly unlikely that atoms and molecules did not exist. So he had never seen them, but he said you can take this in empirical evidence and you can say, well, because of this empirical evidence, we can say something about the existence of things that we cannot see. Now, the link to us being, of course, the same equations. If you don't know the size of the objects that are undergoing Brownian motion, but you can measure the speed of the diffusion and you know Boltzmann's constant, then you could calculate the particle size, which is the technique that's applied in our dynamic light scattering techniques. So this is using the same physics. But it got me thinking, and the article thinking, what is the nature of science? Is it enough to say something exists because you've got multiple measurements of it? Do you have to say they exist? Or is it important if they exist in the end? What happens if they don't? Does that then discount the science? And of course, it doesn't. The observations are still good, and the predictions you make from those observations are still good. It's just you end up with an observation that doesn't fit, and you have to build on that. And that's how science works, doesn't it? I think Einstein, again, standing on the shoulders of giants. And so it's what they call empirical adequacy that's important. Can I build theories that allow me to understand and manipulate the world in ways that are useful to us, that allow us to build models and extend our understanding and understand the properties of the world around us? So it's not that things are right. It's that we have a hypothesis that we can build on. And then when we get to the point where we find it doesn't fit, we go and build something else.
Yeah.
So
do we have an example of that,
yes,
Paul? Do we have an example of that recently?
Oh, well, there are two things I thought. Well, recently, I think we were discussing earlier on that a new force of nature has been proposed because observations of the properties of neutrons don't fit the standard model. And this really interests physicists because they're going, well, if it doesn't fit, then maybe there's something we don't understand. And so that's an example of physicists deliberately testing a model and trying to find when it breaks down, because it then releases the opportunity for other understanding. But I also thought it says something about the science we do, because often when we're engaged with customers, they say, is your technique accurate? Prove to me from fundamental first principles that when you say that the structure of this crystal is really like this, that you absolutely know it precisely, or that the particle size is X. And I was thinking, well, no, actually, that what's important for us is being able to give information, scientific information, as good as we can make it, that then informs a decision or a process for the progress of a project. So to develop a new catalyst or to create a new drug substance. So empirical adequacy, knowing that the technique is good enough for the job, that's what's important, not is it absolutely accurate. And of course, there are areas where you want to ask that, but I don't think that's true in the kind of science we do. So I thought, yes, we get that, because it's correlation and being able to fit the results from our techniques to the results from other techniques that, Malvern Panalytical don't sell. And when we make those links, we know that we enable customers to make leaps in their projects. So I don't know, Steve, how do you view that from a standardization point of view? In fact, both of you are involved in standards development. I think it's important.
I was thinking when you were talking through your piece, yes, it brings into really orthogonal techniques and validation, which is when you're sort of checking something. So laser diffraction, it's good to get some images there to prove you haven't damaged your particles when you actually size it. So have you got nice needles, or have you smashed them into tiny little fat chunks? So image analysis will tell you that, laser diffraction won't. So it's using different pieces of information to validate the result from another, like you were saying Perrin did. The same thing holds true today.
Or with XRD, we see that a particular set of polymorphs are present, but we can see the crystal habit using image analysis. So we get another way of linking the properties of materials and then saying something about a process or a
there are famous phenomena describing how you say it. There's a parameter in crystallinity of polymers looked at with different technologies, and they all come up with a small difference in how crystalline things. You can do it with solid state NMR, you can do it with differential scanning colorimetry, you can do it, of course, with X-ray diffraction, and it all gives a slightly different number for the crystallinity, but it's all is true. But you get a bigger and a greater and a more comprehensive picture if you take all these techniques together, because then you really know what the crystallinity differences are when you look at it. So that's I fully agree. That springs in my mind.
So I'll give you this quote, and maybe this rounds up. This is what Perrin said: "Our wonder is aroused at the very remarkable agreement found between the value derived from consideration of wildly different phenomena." And I love that. Our wonder is aroused when we start seeing these correlations. And I don't know about you, by working here, it is the fact that our wonder is aroused when we get engaged in applications to start connecting things that really is something that drives me, and I know talk to you guys it's similar.
Well, I was just thinking maybe it's worth asking our listenership for other examples of which, like Paul had gave, of where the belief was ahead of the science. Because I can think of a couple, but we'll just ask for people where people believe something was true, but the science wasn't quite there. It may have caught up now, but what do we necessarily believe that what people have believed in the past that the scientific evidence hadn't quite caught up to? And please email us or get us in contact with the usual ways of what you think are good examples of this, and we'll talk about that next time.
Excellent question. And in fact, I think that brings us to the end of this edition. Please, viewers, we hope you've enjoyed this random chat between three geeks. And as Steve says, come back to us with feedback. We're really interested in what you think. You can agree with us, you can disagree with us, you can be somewhere in between. We're just interested. And if you've got other topics that you think it would be great for three geeks to look at and talk around, then post those through as well. But otherwise, it's goodbye from Taka.
Thank you very much for...
And goodbye from me. Yeah.
And goodbye from me. Okay. Look after yourselves, everyone. Bye-bye.
Cheers all.
Bye.
Bye.